Hello everyone, welcome to the today's class. So now I am going to start the GATE question paper of the year 2019, and as I am doing only the organic part I am doing 5 questions in each class. So this time I will be doing question number 9 to 13. These are the organic questions from the GATE question paper year 2019. So let us start with the question number 9. So the question says the major product formed in the following reaction is. So here we are having a non-Bourneil system where there is alkene and we have OTS. OTS you know is excellent leaving group, and you are reacting with acetic acid, and you want to know what is the product form. So these are the various choices given. So basically this is example of formation of non-classical carbocation. So it is here a carbocation will be formed, but not by normal means. What I am trying to say is the conjugation which happens is not normal, but bit different. Let us see what I am trying to say. Here if OTS leaves, you get a carbocation. If the stabilization happens by the neighboring carbon, if it has a p orbital and this goes and overlaps, that will be classical carbocation, okay, stabilization. But here what is happening is basically the orbital, this p orbital is there, the pi bond is there. So basically it means there are 2 p orbitals. So there is an electron cloud here. So this electron cloud goes and helps in stabilizing the anti-bonding orbital if this OTS leaves, okay. So it will help in removal of this OTS. So it is neighboring group participation and my non-classical carbocation means, okay. So what we are doing here is, first let us see, let us try to make it by normal methods. So this pi bond is going and attacking here, you understand, this is not on carbon number 2, but carbon number 3. So spatially it is close to this leaving group, but not exactly next to the neighboring group, next to the leaving group. So once this carbon goes and attacks, so what happens, there were 2 p orbitals, this p orbital had 1 electron and this p orbital had 1 electron. Now this p orbital has taken both the electron. Now this p orbital has taken both the electrons and it is attacking this. So this p orbital is vacant now. So the p orbital, this carbon gets positive charge because it has lost 1 electron, and the bond is formed here and you get this, and then this moves out here, you can here, and you get positive charge here. So last you can again draw like this, how it had started. If the leaving group leaves, you get a positive charge. So basically this is the non-classical carbocation. A carbocation is there, it is spread between 3 atoms which are close to each other spatially, but they are not neighboring, okay, and you get a positive charge. So now basically this p orbital has HOMO filled pi orbitals, HOMO you know highest occupied molecular orbital. So this is what gives electron, and this is the LUMO anti-bonding orbital. So there it gives electron, so that this OTS leaves, fine. OTS is a wonderful leaving group because the negative charge on oxygen is stabilized over sulfur and 2 oxygen atoms. So once this is formed, there is a non-classical carbocation. So all these are bound. So acetic acid cannot attack from this side, please remember this, because the pi orbital is actively taking part in the neighboring group participation, and therefore acetic acid has no other option but to attack from the other side of the NGP, and thus you get retention of configuration. So the answer is B, right. Let us move to next one. Next one says the Woodward-Hoffman condition to bring about the following transformation. So you see here it is the open chain system. Whenever you count how many electrons are there in the pericyclic reaction, you have to see for the open chain system and not the cyclic system. So this one is open chain and this one is pericyclic reaction, basically electrocyclic rearrangement, and you are getting this product. So one ethyl is going towards the viewer and one ethyl is going away from the viewer, and you have to find out it is happening as a thermal condition or photochemical condition. Is it happening conrotatory or it is happening disrotatory? So first we have to find out if it is conrotatory or disrotatory, that we have to look into it and find. Once we know that, then we will know that it happens photochemically or thermally, and I will try to explain it using molecular orbital theory, right. So, this is your starting material, right. So, this carbon which they showed only ET, this carbon sp2 hybridized. So, they had shown ET this side, but carbon valency is 4. So, one hydrogen is this side, and this side also they have shown ET this side. So, one more hydrogen is there, this is this side, because the carbon is trigonal planar in shape. So, 1, 2 and 3, this is the shape how it is trigonal planar, and from there it is becoming here. So, that this ET, if you imagine this ring is on the board, on the screen. Okay. So, what you are seeing, that H is coming outside the screen, this ET is behind the screen, and see here this ET is outside the screen, and H here which I have not drawn, but basically it is there, H is inside the screen. So, we have to find out how do we rotate it so that we get this product. You cannot have a gate question paper or net question paper without pericyclic reaction. Generally electrocyclic reaction always come. So, this is a very simple, once you understand you will never forget, but sometimes it takes time to understand. So, think about it, understand and then move ahead. So, basically what you want here is, let us look at it again. What you want is this ET should come towards the viewer. Imagine if you are rotating this molecule like this, 90 degrees you put. So, what you will see, this ET which is towards the viewer, ET means ethyl group, and this hydrogen which is away from the viewer. So, if I rotate 90 degrees, so that this is still planar, this ring is still planar, but it is coming 90 degrees to the screen. So, this ET comes up and H is coming down, you understand. So, you will get something like this. If I can draw it something like that, okay, I do not have much control over it, but yeah, something like this it will be. So, ET is on top, ET is on top, and H is below, and H is below. So, what happens now, if I rotate 90 degrees, I make it sleep on the board. So, what happens this time, this molecule comes and sleeps on the board, this ET is coming towards the viewer outside the screen, and this H is away from the viewer, that is inside the screen, right. So, you are having this, what do you want? You want ET to come towards the viewer, you want ET to come towards the viewer. So, basically you want it to come up. For it to come up, what you have to do? You have to rotate it 90 degrees like this. This p orbital which has to rotate. So, this p orbital is perpendicular, it is coming like this. You want it to rotate like that, so that it comes and forms bond here with the other one. Okay. So, right now I am making it look like it is a planar, everything is on the screen, you understand this, everything is on the screen. That means, this p orbital has to be perpendicular to the sp2 hybridized orbital. So, this is on the screen, this is on the screen, and this is on the screen. That means, this p orbital is coming, one lobe is coming outside the screen and one lobe is going inside the screen, right. So, now what we do is, I am trying to get it in the plane. So, it is outside the screen. So, I can rotate it either, you understand, this part is I can rotate it either like this 90 degrees, or I can rotate it like this. Which way ever I rotate, what I want is that ET should come out, ET should come out. So, imagine if this is coming outside, this p orbital is coming outside. So, if I rotate it like this, if I rotate it like this, so what happens? Basically what you want is this ET has to come up. So, if you rotate it like that, then what happens? This ET comes up and this H goes down, right. You appreciate my point? A better way to understand will be, maybe let me try this. Okay. So, let us put this behind, let us put this in the, so this is going behind, right. Let us see like this. Okay. So, this H is going inside the screen and this ET is coming outside the screen. This is definitely better way to understand. Okay. And this molecule is not on the screen, this molecule is perpendicular. So, it is going inside, this carbon is going inside the screen, it is planar, you understand this planar. Oh, I am so sorry. Yeah, it is inside the screen. So, perpendicular. So, this p orbital is on the, it is on the screen, it is on the screen 90 degrees. Okay. So, now if you rotate it like this, rotate it like this, so what happens, this is down, so this is coming up, this is coming up. So, how you are rotating, this is down, so you are pushing it up, right. So, it is clockwise, clock rotates like this, anti-clock would have been like this. You are rotating in such a way, please pay lot of attention, you are rotating in such a way, forget the p orbital, just think about this ET. You are rotating in such a way so that the ET comes out. So, you are pulling it up, you are pulling it up only 90 degrees. So, definitely it is clockwise. Now, here what I want is this ET has to go behind the viewer, right, ET has to go behind the viewer. So, what I am doing, I am going to rotate it like this. If you are seeing it this on the plane, imagine you are seeing this molecule on the plane. So, what you have to do, you have to rotate it like this, so that ET goes behind, H comes front. Or if you want to push it behind, if you want to push it behind, so what happens, now this ET is left, you want it to go down, because away from the viewer means down, then you have to rotate it like this, right. Am I telling right? Yeah, yeah. One sec. Please understand, this H has to come up, this H has to come up, and so that ET goes down, you understand. So, what you are doing is you are pulling it like that. So, this is clockwise, this is again clockwise, right, this is again clockwise, and you are rotating like this is again clockwise. So, you are rotating, this p orbital was there. So, what happens is, if this p orbital was there, imagine this is this p orbital was like that. So, this p orbital rotating like that, so that this H comes up and this ET goes down. Okay. So, when you are rotating like this, what it is? It is this is again clockwise. So, this is also clockwise, this is also clockwise. So, when you are rotating both of them clockwise, it is called as con rotation. I hope I made myself clear. If it is not clear, I will try to repeat once again. Okay. Understand this part, understand this part. Let us look at it as if this is in the plane of the board. Okay. Let us not lift it, this is in the plane of the board. What I want is basically H to go down, ET to come up, so that ET is front, because we saw that ET has to be towards the viewer, and H goes away from the viewer, H goes away from the viewer. So, it becomes perpendicular to the screen, so that it becomes perpendicular to the screen. Right now, it is on the screen, this is also on the screen, but what you want is ET has to come front and H has to go behind. So, you are rotating it like this, or so what you are doing is basically, you are pushing the p orbital like that, so that ET comes front, H goes behind, fine. So, this is definitely going like that. So, this is how clock rotates. So, this is clockwise, very clearly this one rotates clockwise. Now, here what I want is, now this is again in the plane, what I want is H should be away, H should be toward the viewer and ET has to go away from the viewer. So, understand. So, this is on the plane, you are rotating exactly 90 degrees. So, a little bit you push behind, you understand, H you are getting front, H you are getting front. So, when you are getting H front and this ET goes behind. So, basically you are rotating it like that, is going behind. So, this is again clockwise, this is again clockwise, you understand, this you are rotating like that. So, that this goes behind and this comes on top, this comes front, you understand, it just goes behind, this comes front, and that is how you are forming the bond, that is how you are forming the bond. So, both of them are rotated clockwise. So, it is called as con rotation. Now, one simple formula you will remember, if you remember you will be able to do everything. How I remember is always, I remember this word 4n h nu dis. With this you will be able to solve all of them, because they are basically 4 systems, 4n system and 4n plus 2 system. These are 2 system. Now 4n can reaction can happen either in the photochemical condition or thermal condition. Similarly 4n plus 2 can undergo reaction in photochemical condition or thermal condition. So that's what we have to find out. Okay. So imagine 4n H nu is dis. So in photochemical condition, if it rotates dis rotation, so under thermal condition it will be opposite, it will be con rotation. So you need not mug this, you have to just mug one of them, you will be able to solve others. Now 4n plus 2, because 4n H nu is dis, so 4n H nu will be con, 4n plus 2 H nu will be con, and 4n plus 2 H nu is con. So of course 4n plus 2 thermal will be dis. What we saw in this question? This question was 4n plus 2 system, because 6 electrons were there. 6 electrons is 4n plus 2, where n is equal to 1. So 4 into 1 is equal to 4 plus 2 6. So 4n plus 2, and it was con rotation. That means very clearly, since it is con rotation, it will be photochemical in nature. Let us try to understand using frontier molecular orbital picture. So this is the one. What do we do is, we have to draw the molecular orbitals of 6 orbitals. Okay. So there are 6 p orbitals, because you saw 3 pi bonds were there, each pi bond means 2 p orbitals. So 6 p orbitals are there. So it will give you 6 molecular orbitals, which I have shown by psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. And as we go from psi 1 to psi 2 to psi 3, psi 4, psi 5, psi 6, energy increases. You can see, you can see energy is increasing that way. Now how do we do? We have to always make nodes. So in psi 1 there will be no node. That means all the orbitals in the one side have same sign, and they don't change. So here top I have put plus, so all of them are plus. So orbitals overlap here very efficiently. That's why it is more stable. Okay. So look at the terminal. Terminal is what is needed. So in terminal carbon, so this carbon which has to form bond, right? Finally at the end, these two carbon has to form the bond to form the sigma bond. So in psi 1 it is plus and plus, okay, the terminal. In psi 2 it is plus and minus. So even if you don't draw, because in competitive examination you need not draw whole thing, you should just be able to draw first as fast as possible. So you just remember this, first you will plus plus, then plus minus, again plus plus, then plus minus. But basically what we want is nodes. So first one had 0 nodes, second one will have 1 node. Symmetrically in the center you put a node. So at the node sign will change. So this is plus plus plus, so they overlap, and then a node comes, so here sign will change, minus, so minus minus minus. So you see here overlap was very efficient, here overlap has reduced, and therefore it is having more energy, it is less stable and therefore has more energy. See, so here it was plus and minus. Now you come to psi 3. Psi 3 will have 2 nodes, so we are making one node here, one node here, and now plus plus, then minus minus, then again plus plus. As soon as node comes, sign has to change. Then psi 4, again it should have 3 nodes, so 1, 2 and 3. So plus minus minus, because here node is not there, then again node is there, so plus plus, again minus. So basically here it was plus and plus, here you got plus and minus. Similarly if you come here, you will have again plus and plus, and finally you will have again plus and minus. So see here on the psi 6 you have 5 nodes, so everywhere sign is changing. So it is plus, then here it is minus, again plus, then again minus, then again plus, then again minus. Okay. And whatever is top you will be writing opposite down. Now you have to put the electrons. How many electrons are there? Since 3 pi bonds, so 3 2s are 6 electrons. You know, in each atomic orbital or each molecular orbital maximum 2 electrons can go. So psi 1 2 electrons, psi 2 2 electrons, psi 3 2 electrons, right. Now psi 4 is empty. Now psi 3 is called as HOMO. HOMO means highest occupied molecular orbital. So, you see psi 1, psi 2 and psi 3 has electrons. So, they are occupied molecular orbitals, HOMO. In them which has highest energy? Psi 3, fine. And then LUMO, LUMO means lowest unoccupied molecular orbital. So, psi 4, psi 5 6 and psi 6 does not have electrons. So, they are all UMO, unoccupied molecular orbital, and this is lowest energy between psi 4, psi 5 and psi 6. Psi 4 is least energy. So, this is LUMO. Now, you understand, for this electrocyclic rearrangement to happen, only that orbital which has electrons can take part. So, this will rotate and this will rotate. So, HOMO is what we have to look for. So, under thermal conditions, when you are having only heat, our question does not say heat, our question says we are having photochemical conditions. So, light is there, but under thermal condition, this is the ground state, and ground state is what we would have considered. So, this is the ground state. So, we should have considered psi 3, but here it is saying it is photochemical condition. So, we have to look at excited state. So, when you put photochemical condition, when you put light in it, then the electron goes, one electron gets excited and moves from HOMO to LUMO. So, what has happened? Now, here one electron is there and here one electron is there. Please remember, reaction will always happen only from HOMO and not from anywhere else. So, now this is what is HOMO. So, in the HOMO what do we have? We have plus, minus, and here we are having minus and plus. We are not bothered about other things, we are only bothered about this, because these two has to interact to form the bond. So, now what happens? Let me draw it separately down and then I will show you. Yeah. So, this is what has happened. Psi 4 is the new HOMO under photochemical condition. Now, for the reaction to happen, plus has to meet plus or minus has to meet minus. So, imagine if this is going behind, okay, and this p orbital is exactly on the plane. So, this part is perpendicular to the screen. It is still planar, but it is perpendicular to the screen. So, this p orbital is on the screen. So, top was plus, minus, here top is minus and plus. For the sigma bond to form, plus has to meet plus or minus has to meet minus. Plus cannot meet minus, minus cannot meet plus. So, what happens? This one will rotate like that 90 degrees. So, this is clockwise, and this one also will rotate only 90 degrees, it will rotate like this. So, this is again clockwise. So, that is why under photochemical condition, 4n plus 2 system goes con rotation, and here we got that product, fine. So, the answer was D, which is photochemical con rotatory. Moving on to the next question. This question took so much time for me to solve. It was such a simple question. How they tried to fool you is they wrote of benzene. So, the thought comes is benzene must be solvent, but here benzene was not only solvent, it is also reactant, and here they did not write AlCl3, they wrote Et2AlCl. So, this is also kind of AlCl3, but they have made it organic so that it dissolves easily in organic solvent and a reaction takes place. So, now if you see this reaction, it becomes very clear. So, what is this kind of reaction? So, there is a benzene, and you are having ester. So, it is kind of a Fiddlecroft acylation reaction. Okay. Generally, acylation means we use anhydride or acyl halide, but here also this can break. So, it is Fiddlecroft acylation reaction. So, let us look and see what happens. Yeah, so it was Fiddlecroft acylation, all that I said is there. So, you know, Al has 3 electrons. So, 3 plus 3 total 6 electrons. Octet is not complete, one orbital is free. So, it acts as Lewis acid, it can accept lone pair of electron, and therefore, this carbonyl goes and gives electron and you get positive charge on carbon. Now, what happens? First of all, oxygen is electronegative, it pulls the electron very strongly towards itself. So, you get a positive polarity here. Now, oxygens get positive charge. So, electronegativity, you understand what is electronegativity? Electronegativity is tendency to attract electron. First of all, it had a tendency to attract electron. Now, positive charge. So, it badly wants electrons, it pulls lot of electron. So, lot of positive charge is there. So, it becomes very electrophilic in nature, and nucleophile will be more than happy to attack on this carbon. Fine. Let us move ahead. So, that is what happens, and this is what you get, and now you have benzene ring. Now, benzene ring acts as a good nucleophile. You will say benzene is very neutral, does not have any polar carbon, no lone pair, how? But what happens, you understand, benzene is a planar molecule, it has p orbitals, all of them have 1 electron. So, 1 electron here, 1 electron down here, up. So, lot of electron density up and down of the plane of the ring of benzene, and this electron density is what favors the reaction. So, this pi electron goes and attacks on this carbon, and this goes up, and you get here, and this positive charge is stabilized by, you see here, you get a positive charge on this carbon, because initially both of them were sharing 1 electron. Now, this carbon took 1 electron from this carbon, gave off to this carbon, kept its own electron here. So, this remains neutral, this one got electron, so it goes up, though this carbon gets positive charge, and you are getting O minus CCl3. Okay. And then what happens? You have to show stabilization of this positive charge. Why it forms? Why benzene undergoes? Because its transition state is not unstable. If positive charge in one place, very unstable, but it is delocalized over a lot of location, so it is stable, it does not mind being there. So, this pi electron goes here, you get positive charge here, then goes and attacks here, you get positive charge here. So, that is what is happening. And then what happens? This pi electron cloud comes here, and you get bond here, right, and you get bond here, and then this again, this comes down and this comes up. So, basically this ester opens up, and you are getting this ketonic part, and you are getting this O minus, which takes away takes proton, and you get alcohol. This is a catalyst, remember, this catalyst will come out unreacted. So, aluminum was having negative charge. So, this comes down, and then this leaves out, and you are getting this, and thus the answer is B. Moving on to the next question. Now, they made it very simple question, but I will try to explain whole thing, because my aim is not to teach you, not to make you solve this question, but teach organic chemistry through this question. So, what they said is, in the following reaction, stereochemistry of the major product is predicted by Cram's rule, Felkin model, Felkin-Ahn model, Cram's chelation model. What they are doing is, there is a carbonyl group, alpha to carbonyl group, there is a chiral center. Now, when you attack with nucleophile, so you will get always some amount of stereoselectivity. ET will attack from one side more favorably than other side. You know, lithium is the metal, so lithium will have positive polarity, because metals by definition they are electropositive in nature. So, they always give electron to give positive, and ET is negative. Now, ET can attack carbonyl, please understand this part. ET can attack, ET minus can attack this carbonyl either towards, like from outside the screen it is coming attacking, so from towards the viewer, or it can attack from behind the screen, so away from the viewer. So, because chiral center is there, one of them will be preferred, either it will prefer more from front or more from behind, and that is what gives you stereoselectivity. It does not give stereospecificity, not only one, it will give both, but one will be more favored. So, one will be major, other will be minor. So, generally what happens, you can find out by either this method, Cram's method or Felkin-Ahn model. Felkin model is same thing, but Felkin-Ahn is what we do. But Cram's model is what we see is, what we do is, we put bulky group and this something like CPH on the same plane, and then we try to look at it. So, that is what initially Cram had suggested, it always gave right result, but the model itself was wrong. And later, because they could study the transition states with various NMR techniques, and they came up with Felkin-Ahn model, where they said this, the bulkiest group is 90 degrees to C double bond O. So, though both gives the correct answer, but we always, now we don't talk about Cramp's model. Why? Because Cramp's model is outdated. They did not know the transition state correctly. So, we should always talk about Felkin-Ahn model. If you see any modern book, something like even Claydon, they don't talk about Cramp's model. One small line will be there about Cramp's model. They always talk about Felkin-Ahn model. But interesting thing is Felkin-Ahn model also says that, but what they were asking for is basically this chelation word. Here it neither follows Cramp's model or Felkin-Ahn model. It is basically chelation model which is followed. So, because lithium is there, because lithium is a very hard metal ion, it will chelate with this oxygen and with this oxygen, because both of them are lone pair, and this chelation is what is determining how will be the stereoselectivity. So, the answer very clearly is Cramp's chelation model, but let us understand how does it work. Okay. So, again I will not teach by Cramp's method, it is fine, it does not matter. So, I will talk about the chelation. So, what happens basically is, you want this C double bond O and this OCH3 to be eclipsing each other. If this oxygen and this oxygen come in front of each other, this lithium will be happy to coordinate them, and that is how stereoselectivity comes. Whenever bond is formed, understand, some energy is released, stability is gained. If Li plus is there, so this lone pair goes and interacts with it, this lone pair goes and interacts with it. So, they both interact, energy is released. So, that is why chelation is preferred. So, let us first know how to draw various conformers. Fine. So, initially that is what they had given. So, I am also drawing like this. So, what you are seeing is this C double bond O is in the plane and this C and pH is in the plane. So, basically they are eclipsing each other. So, what you can do is you draw it like this, and what you can do is put here C double bond O, and this pH is in front basically. So, you draw pH like that, right. And then what happens is, this pH is eclipsing this C double bond O, right. You can see that. So, you draw pH here. Now, what happens is this OCH3 is coming outside the screen because it towards the viewer, and this ethyl is inside the screen, correct. Now, imagine I am looking from this side. So, what do I see when I am looking from this side? I should draw it other way, okay, because I am looking from this side. I could have looked other side, but let us view one way. You should have very clear, you should have lot of clarity about stereochemistry, how to look and what to look. So, you are looking from this side, you understand. So, when you look from this side, what you are seeing? You are seeing pH in the plane, and you are seeing C double bond O in the pH on the plane and pH behind. So, if I am looking from this side, what I am seeing is basically C double bond O is behind, and pH is also behind. So, pH is in the plane. I can draw like that, correct na? What else I am seeing? I am seeing from here that pH is eclipsing this. So, pH you draw exactly in front of this O. I am drawing little bit like that, because if I put on that, you will not be able to see. And then what you are seeing? You are seeing from this side that OCH3 is coming this side and it is coming this side. So, if you rotate this, you understand, you catch this pH and move it behind, because you are seeing from the front. Then what you are seeing, that OCH3 is on this side and it is on this side. It is on the left side, OCH3 is on the right side. Please do not move ahead if you do not understand. Think about it, understand, then only move. What I have done is I have caught this pH and pushed it behind 90 degrees, so that you are seeing from the front outside the screen, and what you are seeing is, you are seeing in front of your eyes pH, and behind pH you are seeing C double bond O. So, that is why I have drawn C double bond O, pH front, and this pH is going behind, which I have drawn here. Now, from the front I am seeing pH. So, when I am seeing from the front, I am seeing this OCH3 this side. So, I am going to draw OCH3 this side, and ET on the and ET on the left side, ET on the left side, okay, ET on the left side. So, this is what I drew. How did I draw right? One second. I have drawn OCH3 on the left and ET on the right. Oh, something is wrong. Here what has happened is, here I am looking C_O towards the viewer. There I have put C_O away from the viewer. Does not matter. Either way it should be fine. That's what clarity of thought should be there. There what I have done is, I am starting looking from this side. Start looking from this side, then you will get same thing what I have drawn. So, maybe I will do it like this also, so that you get clarity, and that is how I have solved the question. So, let us do it like that. Okay. Let me draw it again for you. If I look from this side, basically what I am saying is, if I am looking from this side, I am pushing it behind, so that this is coming outside the screen, and I am looking from front of the screen. You are looking from the screen. So, when you are seeing directly what you are seeing, you are seeing pH in the front and C_O. So, what I can draw is, I can draw C_O here, and pH is down. So, I am looking pH down. You understand? I am looking from this side. So, I can continue looking from this side, or I can just pull it front 90 degrees only. So, that this whole molecule goes behind, and you are having C_O on the screen, C_O on the screen, and this pH coming outside the screen, this pH coming outside the screen, and this whole thing is going behind the screen, but exactly in the same plane, because it is sp2 hybridized. This whole thing is trigonal planar, and you are having C, pH and everything. So, what happens now? What you see from here, pH is in the plane. So, you draw pH here, you draw pH here, and then what you are seeing, when you are seeing from this side, this OT is going this side. So, you can draw OT, ET here, not OT, sorry, ET here, and you can draw OCH3 this side. This is what I have taken. Either way is fine. What I drew beginning also is fine. What I have drawn now also is fine. It is just that angle of looking. I am looking from the left or from the right. So, now what we want is, this O and this OCH3 has to come in same plane, so that lithium can chelate with it. Chelate is basically coordinating with more than one ligands. So, what I am going to do is, I am going to rotate this by 60 degrees. So, when I am rotating this by 60 degrees, OCH3 comes up, pH goes in place of ET, and ET goes in place of OCH3, right. So, that is what is happening, and you are getting this. Now, lithium will go and coordinate with it. So, lithium goes and coordinates, it fixes it. Now, it has no other option but to react in this conformation. Now, the nucleophile is coming. Now, tell me, nucleophile will attack this C_O, that is how it happens, because it is the nucleophilic center. Now, tell me, this nucleophilic will be happy to attack from this side. It has to basically attack from 107 degrees, close to that 109 degrees. No, it is called as Bond-Durji angle. So, it is 107, you can think as 109 degrees, because that is what is tetrahedral angle. So, you think it will attack from this side, or it will attack from, or nucleophile will attack from this side. It will definitely attack from here, because ethyl is small, it has only 2 carbons. pH is much more bulky, it is having 6 carbon. Therefore, attack will happen here, and OH will come here, and nucleophile will come and attack here. So, what is the nucleophile? ET minus, because it was ETLI. So, ET minus comes and attacks here, this O comes here. So, OLI, ET, and this pH remains here, and you get this. So, this is the product. So, the answer was B, that is Cram's chelation model. This chelation was important. Now, last question for the today's class. The product formed for the following reaction are. So, thermal and photochemical, no, generally it is pericyclic reaction, especially if you see something like this. So, this is sigma-tropic shift, it is called as 3,3 sigma-tropic shift. Okay. Why it is 3,3 numbering, you have to remember. Okay. Now 3 is important, you have to just count 3 means 3 plus 3 total 6 pi electrons involved in the transition state. So, if 6 pi electrons are involved in the transition state, it is following Huckel's rule. So, it is going through aromatic system through aromatic transition state. So, it is thermally allowed to be symmetry allowed, okay. Otherwise, it is not symmetry allowed if it is not following Huckel's rule. So, generally then it is photochemically favored. Now, why it is 3 because see here basically what happens is this bond opens up here, this bond comes here and this bond comes here. So, what you are doing is you are breaking a bond, you are breaking the bond in between these two, right. So, wherever you break, no, you start counting both sides. So, 1, 2 and 3, here you also start counting. So, 1, 2, 3, and wherever the bond is formed, no, at that what you had given number initially, that same number will stay. So, what happens, this bond comes here, this bond comes here, this bond comes here. So, basically you are forming bond here. Whatever the number initially it had got 3, this also got 3. So, it is 3 sigma tropic shift. It is also called as co-rearrangement because there is only carbon-carbon bond. If oxygen was there, it would have been called oxycope. If nitrogen was there, it would have been called azacope. When nothing is there, just carbon-carbon bond, it is sigma tropic shift happens, it is called as cope reaction, okay. Now, what they asked was stereochemistry. So, let us first understand this. This goes and attacks here. This is the transition state involved. This pi bond is moving. So, this pi bond I am making it like that, like that, like that, spread around. Now, to find out stereochemistry, this 6-member transition state has to be made like chair conformation, okay, has to be made like chair conformation. And in the chair conformation, remember, if in the normal this wedge and dash shape, this is called as Sawhorse projection formula. Whatever is towards the viewer in chair conformation, make it above the plane, and what is away from the viewer, that you have to make it below the plane, fine. So, that is what I am going to do here. So, I have made this 6-member transition state. So, CS3 was towards the viewer, so I have put it above the plane, and second CS3 also towards the viewer, so I have put it above the plane. So, now here what happens is, in chair conformation you have axial and equatorial. So, this is axial, this is equatorial. You know how to reach axial? See, on this carbon to reach you have to go from down to up, here also down to up. Since you are going up from both sides, up will be axial, just make 90 degrees. But to reach this carbon you have to go down from this side also and from this side also down. So, just straight make one line, that will be your axial, and then inclined will be your equatorial. So, this is your equatorial, here also it is equatorial. Now, what you see, you have to compare. Now, this is not planar actually, this is coming outside the viewer. Sorry, this part of the ring, no, this part of the ring actually is coming outside the board, but forget all that, just see at this CH3 is definitely above this hydrogen. So, this is above the plane, this is below the plane. Similarly, this bond, this equatorial bond is definitely above this axial bond. So, this CH3 is above the plane, this is below the plane. So, that is what it is. Now, you do the sigma tropic shift. So, this comes here and this comes here, you get the bond. So, what you are getting, you are still getting CH3 above and here also CH3 above. So, this is the product form. So, they asked you E and Z. So, you have to give numbering E and Z. E and Z is very much like cis and trans. E is trans, Z is cis. So, you have to look across the double bond. So, this is the double bond, you have to look at this carbon separately and this carbon separately. So, on this carbon, you have to give preference to the substituent. So, you will give according to atomic number. So, here there is hydrogen, here there is carbon. So, which has higher atomic number? Of course, carbon. So, this gets first preference, this gets second preference. Here also you look, this is carbon, this is hydrogen. So, this gets first preference, this gets second preference. So, what do you see? Both first preference on same side, both second preference on same side. So, this is Z this is Z. But here on this what happens is this CH3 gets first preference, hydrogen gets second, this alkyl groups gets first. Okay. So what happens, this first and this first is across, this second is across. So this is Z and this is E. So your answer is, so this is your answer. So E and Z. So answer is C. Okay. So that's it for today's class. Thank you very much. Bye bye.